Okay, so the next question we have over here is this one. In the given reaction, 2Fe plus 3H2O gives Fe2O3 plus 6H plus 2 electrons. Okay, so what is Fe2O3? What do we call Fe2O3? Like, what mineral is it?
Hematite.
Sorry, your both voices actually coincided. Hematite, right? Fe2O3 is hematite, Fe3O4 is magnetite. So this is basically a hematite reaction. And also, okay, in the question also it is mentioned Fe2 plus 2 hematite boundary it is asking. So let's first have a look at the question. Consider ideal condition. Take concentration of Fe2 plus as 10 to the power minus 5 molal. Molal is, there is a molar concentration and there is a molar concentration. So molal is, it's just that it is taken out of directly weight of the solvent, and in molar we take out of volume of the solution. Okay, so there is not much difference over there. E naught is 0.98 volts, pH is 6. Then this is given value of 2.303 RT by F is 0.059, where F is the Faraday constant. Then it is asking the value of EH on the Fe2 plus hematite boundary at 25 degrees centigrade is. Okay. So firstly, this question is actually based on Nernst equation. If you must have heard about it, I don't know. Let's discuss it over here. This question is directly based on Nernst equation. Okay. You all should know this equation. You all should remember this if you are appearing for GATE. And maybe they can even ask this if you are appearing in JAM. So maybe like anytime next they can ask this question based on this in JAM as well. In CSIR NET, in GSI prelims and in GATE, question is expected out of these kind of concepts. So you must know this Nernst equation and you must know the concepts of EH-pH, electrode potential and the pH, EH-pH diagrams. So EH-pH diagrams are directly derived from this Nernst equation itself. Or you can say Nernst equation is derived from the diagrams. So this is reversible actually. So here in this case, we have somewhat this kind of a diagram, this kind of a graph. I will draw it here. Somewhat this, okay. This x-axis is the pH axis, y-axis is the EH axis. All right. So this particular curve or this line is given by Nernst equation. Right. Just 1 second, someone is joining. So this line is given by Nernst equation. Right. Here it is saying that pH is given to be 6. So basically, if we take somewhere around here, just 1 second. If we take a line from here, so if pH is 6, what will be the corresponding EH? It is asking. All right. So this corresponding EH we don't know, and we know that pH is 6. So the general equation, the general Nernst equation that we have is EH is equal to E naught, sorry, E naught, or here also you can write E, only E, so that is nothing but EH. EH is equal to E naught plus 2.303 RT by NF log base 10 Q. Okay, so this is the Nernst equation. Here, what is Q? Can anyone tell me? What is Q?
Equilibrium constant.
No, Q is actually reaction constant. Equilibrium constant is K. Okay, Q is actually reaction constant. K is the equilibrium constant. Okay, so don't get confused here. We'll come to these two. Q is reaction constant. And we have taken log, we are not taking ln because 2.303 is already written over here. So actually this I think I already mentioned. I will write it again here in short. So you have to remember this thing. Ln k, if let's say there is ln k, this is nothing but 2.303 into log k. Okay, log base 10 k. Ln is log base e. So this is the basic like log concept. So this you must remember. If you have 2.303, then you will write log base 10. You will not write ln. Okay. So this is the Nernst equation. Now, if we have a look at the question once again, what reaction we have and what can we do around here. Now just have a look. Do we have E naught? Yes, we have E naught value over here, right? 0.98. We need to know the corresponding EH, right? We also have the value of pH. So what does pH signify? If pH is 6, what can it tell you about? If there is some certain pH given to you, what does it signify?
Then minus log to the base 10, H plus value is 6.
Right. So this minus log base 10 H plus concentration. So whatever H plus concentration is there in the solution, if we take the log base 10 and put a minus, that is pH. Okay. So this is the basic pH formula actually. pH is equal to minus log base 10 H plus concentration. So this pH 6 is given to us. We can directly get to know what is the H plus ion concentration in this reaction by using this particular given value. Okay. So if we have a look at the reaction, here H plus is there. So we can use this over here. Then we have Fe2 plus concentration is given. So Fe2 plus is here. This concentration is given. This concentration is given through pH. This concentration is given directly. Alright. Fe2O3, since it's a solid, we will neglect it. When we will solve it, I will just show you how. And then we have this complete value is given. 2.303 RT by F is given. N is not given. So N we have to see through the reaction. Okay. So all these values are given to us. And then log base 10 reaction constant we can directly get through the reaction. So basically everything we have over here for Nernst equation. And also just remember Nernst equation is like when we take this value 2.303 RT by F. So I will write it here. It is already given in the question, but it has a specific condition for it. 2.303 RT by F is 0.0592 actually. It is given 0.059. So if we complete it, it is 0.0592. This is applicable only when temperature is 25 degrees centigrade or 298 Kelvin. Okay. So this is a particular condition for this complete value to be 0.0592. Alright. When you Faraday constant has a value, R is universal gas constant, it has 8.314 as value. You keep T as 298. Only then you will arrive to this particular constant. Okay, 0.0592. So this thing you have to remember because sometimes in questions, maybe you won't be given this value directly as it is given over here. Okay. So it will just be mentioned that temperature is 298 Kelvin or temperature is 25 degrees centigrade. Then you can directly substitute this all these values on the LHS by 0.0592. Okay, so whenever the temperature is this is applicable. So let's go back to the reaction, what reaction we had. Okay, so we have I will zoom in after some time. 2Fe2 plus plus 3H2O gives, just 1 second, gives Fe2O3 plus 6H plus 2 electrons. Okay, so this is the reaction that we have over here. Fe2 plus concentration, we already know it is 10 to the power minus 5. Okay, I will write all the values over here. Fe2 plus concentration is 10 to the power minus 5. pH is 6. Also, what else is given? E naught is given 0.98 volts. So this question is actually from electrochemistry, and electrochemistry is also an important part. Direct numericals come from this part because this is totally formula driven, the electrochemistry part. Okay, so if you remember a certain few things, you can easily solve these questions. These are actually simple questions. So now let's get back to the reaction. The Nernst equation, we had EH is equal to, I will write it again over here so that you don't get confused. It was 2.303 RT by NF. N is a factor that includes the exponent parts, like these parts in the reaction. Okay, so we'll calculate N using these parts. Here we had log base 10 Q. So EH will be E naught, we have 0.98 volts plus, here we can directly write 0.059, right? Divided by N. What will be N over here? Can anyone tell me? What will be N? Now see, here it is talking about where we have to calculate. We have to calculate on Fe2 plus and hematite boundary. Fe2 plus and hematite boundary. So you have to have a look at this Fe2 plus and hematite Fe2O3. So now tell me what will be N?
So 2.
Yes, actually N will be 2. N is just uh, the exponent difference that we are getting. Okay, so it's not also the difference, but the ions that are involved. Here you can see two Fe2 plus ions are involved, and two Fe2 plus ions are now making the hematite. So how many Fe2 plus is getting utilized to make the hematite? So that is what it is asking. It is asking about Fe2 plus to hematite boundary. So two Fe2 plus are getting utilized to form Fe2O3. This is the basic thinking that you need to develop whenever it comes to N. Okay, so here N will be is equal to 2. This is for this particular reaction. Maybe in magnetite reaction it can be different. It totally depends on how many Fe2 plus is getting utilized. Okay, and also here it should be 1, the exponent, if you are taking 2, because here if it is different, then the N value can differ. I think you are getting it. Here actually what we have reactants, we have products, right? Let's say here we have N1 reactants, N2 products. Now how much N1 is getting utilized to produce N2 products? Now N2, if N2 is having some value, then overall N will be how much? Here not actually this. This is what we get for overall n. So this is how you calculate for the exponent part. This is how you take the n value. So here we have, if we proceed with this, now this Q is actually reactants, products by reactants, concentrations of products by reactants. So concentration of product we have H plus, we will have 6 power, right? You need to go through the basics of this. This exponent goes to the power part whenever we calculate K and Q, if you remember. Does everyone remember this? Is everyone getting this? Why it is going to the power 6? Please let me know right now so that I can understand and I can take you through. Then we have Fe2O3. Fe2O3 will come out to be 1. Concentration will come out to be 1. Here it will be power 1 to the raised to the power 1. Since Fe2O3 is a solid, so it will come out to be 1. Its concentration. Divided by, there also H2O we take 1. We have Fe2 plus concentration raised to the power 2. Is everyone getting this part? How we got Q?
Yes, sir.
Okay. So this is an important part, and this is a basic of quite simple basic of calculating K equilibrium constant and Q reaction constant. Whenever you must have studied this, I think it's long time back. If you haven't revised these things, you have studied this in your school days. So these are actually basics. You must remember this. The exponents are taken to the power when we calculate Q and K in terms of their respective concentrations. So here we have again 0.98. I will not write the units anymore. 0.059 by 2. Let's take log inside. Okay. Let's take this log base 10 inside. This will be equal to 1. So this will not be there. So if we take log base 10 inside, what do we have? We have 6 log base 10 H plus minus 2 log base 10 Fe2 plus. Is this equation right? Is this conversion right?
Yes, sir.
0.059 by 2. What shall I write here? 6 log base 10 H plus.
-6.
It will be 6 into minus 6, right?
Yes.
Minus 6 will come in place of log base 10 H plus because we have pH is equal to 6. So pH is equal to minus log base 10 H plus is equal to 6. So in place of log base 10 H plus, this will become minus 6. Minus 2. Again, what will we have here? Log base 10 Fe2 plus. Fe2 plus concentration, we know it is 10 to the power minus 5. Look at the left side top corner. So it will be log base 10. Fe2 plus concentration is 10 to the power minus 5. Okay. So these are now just simple arithmetic calculations, nothing else. The only thing was about n, and if you know the basic concepts of calculating Q, and obviously you need to remember the Nernst equation. So through this, you can easily solve this question. This will come out to be minus 36, then minus 2 Now log base 10, this will bring out -5 outside, and log base 10 to 10 will become 1. Okay. If you don't understand any step, please let me know. Otherwise, I wouldn't know that you are having any doubt. -36, this minus minus will become plus 10. Log base 10 to 10 is 1. Okay. This will come out to be 1. So now what do we have? Let's take this 2 inside. Then we will have -18 plus 5. Into this will be -13. Just quickly calculate this, please. This is EH that we are calculating. Okay, so this is coming out to be 0.213. What it has asked, up to how many decimal places? Round off to 2 decimal places. So it will be actually 0.21. Right? This will be the answer. This will be the EH value when pH is 6. EH will be 0.21. Has everyone got this? Got this question? How to do it? How to apply Nernst equation? How to use the reactions to get N? Why we are not taking concentration of H2O? Actually, we don't take concentrations of this simple water. H2O, we actually are taking H2O. We don't take concentrations of solids. Okay. And when it comes to water, like you must have gone through the details as well. So water and these kind of liquids, these concentrations are taken to be 1. And also for all solids, concentrations are taken to be 1. So because of that reason, we didn't take H2O because it will come out to be 1, same as Fa2O3. So for solids and for liquids like water, these concentrations we take to, like, we take the concentrations of these values to be 1. So 1 to the power 3 would be 1 only. That is why we didn't take it up there. Is it clear? We mostly focus on these individual terms. These are the individual cations and anions, right? So whenever we calculate Q and K, mostly what we take the values of these individual cations and anions, which are not in any compound form, not in any molecular form. And if any molecular form is there apart from H2O, and if it is liquid, then only we take the concentration of it. For any solid molecular form or on any solid compound, we take the concentration to be 1. So always remember these basics. Is it clear, MJ? Okay. Yeah, you replied. Okay. All right. So I hope everyone got this. If not, you can again go through it, and you can go through the basics once. If you require a bit of help, you can go through the basics of this thermodynamics, equilibrium constant, and everything. Okay, so you can easily get it in NCRT chemistry books. So you can get it from there, and also in any geochemistry general book that we prefer for GATE, JAM, everything. So you can go through the basics once if you are finding it more difficult to recall whatever you studied in your school days. Then you can go through the basics for once to help yourself out. Okay. Coming on to the next question, we have the first and second dissociation constants. So these kind of, you can see the thermodynamics and these kind of questions are asked a lot in GATE. Okay. And also in JAM, some of these questions are there. Mole concept, thermodynamics, electrochemistry, and we can say questions based on entropy. So all these kind of things, Clausius-Clapeyron equation. So these things you must remember. You must be well versed with it, with these. This is only about once if you go through these type of concepts again, once you recall these concepts, then it becomes really easier to solve these questions because these are really simple questions. It's just that who knows the concept and who doesn't know it. So okay, here we have the first and second dissociation constants of H2CO3. Dissociation constant is when it is dissociating, like H2CO3 will break down to form some compounds. Okay, so it will break down in two steps to get the final individual compounds. That is why we have first constant and second constant. So I will write it over here straight away. If you see H2CO3, it will break down into H plus. One H plus will be removed. What will be left? We will be left with HCO3 minus. Okay, bicarbonate ion. So this is the first dissociation reaction that is taking place. So we have first dissociation constant. First dissociation constant is this 6.761 into 10 to the power minus 7. Then HCO3 minus will again break down, right? We will have HCO3 minus. This will break down to give us H plus plus CO3 2 minus. Okay, so now we have individual components, individual elements. So now H2CO3 has been broken down completely using two steps, including two steps. So this value we have 4.68 into 10 to the power minus 11. So these two dissociation constants is given. If the concentration of H2CO3 is 1 molal, now it is saying that concentration of H2CO3 is 1 molal. Okay, so we will write it here. Concentration of H2CO3 is 1 and pH is 6. Again here pH is 6. Summation CO2 in the solution is dash molar. It is asking summation CO2 in the solution assuming ideal condition is dash molar, round off to 3 decimal place. Now firstly, what is summation CO2? Does anyone know this? What is summation CO2? Is anyone saying something? Yes, someone raised hand. Dibesh. Issue maybe by mistake. So we take like summation CO2 it is asking. This is totally dependent on H2CO3, the initial compound that we have for dissociation. Now in this H2CO3, what will it depend upon? It will depend upon actually H2CO3, it will be combined effect HCO3 minus plus CO3 2 minus. So this is basically we are writing everything down from where CO2 can be found. Okay. So summation CO2 can be found from H2CO3, like not summation CO2, individual CO2s from HCO3 minus and CO3 2 minus. Alright. So these three we have in the reactions. These three is where CO2 can be found. So now for H2CO3, these are the individual concentrations for these three. H2CO3, we already know that concentration is given as 1 molal. This, let us assume this to be X. Let us assume this to be Y. So if we get X and Y, we will get the final answer. Alright. So now how to get X and Y? How to get the concentrations of X and Y? Summation CO2 is nothing. We need to get the final concentration of CO2 that is involved in the reaction in molars. So this is basically, it is asking about the concentration of CO2 involved in the reaction. So concentration of CO2 that will be involved in the reaction will be based on H2CO3, how it is breaking down and wherever the concentrations of CO2 is there in those individual compounds. So this is what we get. We can get from S2CO3, we can get from SCO3 minus, and we can get from CO3 2 minus. Now S2CO3 concentration we know it is 1. Let's assume this to be X and this to be Y. Now we have to calculate X and Y, then we can easily get the summation CO2. Okay, are you getting this? Because this is the critical step. If you can know how to calculate summation CO2, then you can easily get the answer. Now it has become quite simple if you are getting this step. We had these reactions, right? First reaction, second reaction. So now let's see how to get X and Y. Now using K1, this first reaction, K1, if you use K1, what will be K1? H plus concentration into HCO3 minus concentration divided by H2CO3 concentration, right? Products divided by reactants, and here it will be power 1 power 1 power 1 for all raised to the power 1, because there is no exponents here. This is equal to, given to us as 6.761 into 10 to the power minus 7. Now have a look at this. For H plus, what will it be for H plus? What can we write over here for H plus concentration? What can we write for H plus? H plus will be 10 to the power minus 6, right? H plus concentration is nothing but 10 to the power minus pH. This is coming out just from that log formula. Do you remember this? We have pH as 6. So what will be H plus concentration? 10 to the power minus 6 into this HCO3 minus we have taken to be X. So let's keep it X so that we don't have to write the bigger term again and again. S2CO3 concentration is also given to you 1. So from here we get X. What is X? X is 6.761 into 10 to the power minus 1. Okay. So this is what we have got for X. Just remember this part. This is coming out from that log formula only. H plus concentration is nothing but 10 to the power minus pH. Now coming to K2. K2 is again, if you look at the reaction here, we will take the second reaction. K2 is again H plus, then CO3 2 minus divided by HCO3 minus. Okay, from this reaction, the second one is equal to, its value is given to be 4.68 into 10 to the power minus 11. So again what we will have here, H plus is again 10 to the power minus 6 into CO3 2 minus we took Y, right, divided by HCO3 minus we just calculated. This X was HCO3 minus, right? X is HCO3 minus. So we just calculated, we can put it here. What was the value? Just one second. 6.761 into 10 to the power minus 1 is equal to, we have 4.68 into 10 to the power minus 11. From here we will get Y. Now Y becomes 4.68 into 10 to the power minus 11. So some basic arithmetic calculations. Divided by 10 to the power minus 6 into 6.761 into 10 to the power minus 1. Right? This will come out to be 11, 12 minus 6. Then this will come out to be, just let me calculate. Okay. So we can write it as 3.122 into 10 to the power minus 5. So this is y. We have got y, we have got x. Now you can see y is actually, since it is 10 to the power minus 5, it is having very less effect in contributing to CO2. Okay. This 10 to the power minus 1 is nothing but this is 0.6761. This. And H2CO3 was 1. So if you add this in 1, it will have a significant effect. But now let's see here. What is this? This is 0.0003122. So this will have very less effect on adding, right? And also it is not asking up to that much decimal. It is only asking up to 3 decimal places. So now what will be summation CO2? For H2CO3 we had 1. For HCO3 minus we got this 0.6761. And then for this last one, CO3 2 minus, we got 0.00003122. Now if you add this up, what value will you get? You will simply get, you can simply ignore this because you need to answer only up to 3 decimal places, and this will put an effect starting from 5th decimal place. Okay, so up to 4 decimal places it is not putting any effect. It is starting from 5th decimal place, so you can simply ignore this part. It is asking only up to 3 decimal places. So 1.676 will be the answer. Molal. So this will be the answer for this 1.676. Yes, 3 decimal place. Is this question clear? Please let me know if this question is clear. It was a simple question. It's just that you needed to understand the language of the question, what it is asking. Everyone, are you all along with me right now so far? Please let me know. एटलीस्ट कुछ टाइप कर दो यार कमेंट बॉक्स में. Thank you for typing. Okay, so up to this part we have got 2 questions. All right, so next time when you get such kind of questions, summation CO2 or summation of any kind of oxide gas value, let's say, so you just need to focus on the reactions that you have. Okay, now here you needed to know that you needed to write these 2 reactions. It is not directly given in the question. It is just saying first and second dissociation constant. So 2 dissociation constants means the initial reactant product will break down in 2 steps. So this is the basic thing that you can draw from this information, and then you can simply break it down in 2 steps as we have done here. And these are the 2 constants that are given, 2 dissociation constant values. Okay, and then you can use it accordingly. Now it is asking summation CO2. Summation CO2 means CO2 that is involved in the complete reaction. So it will be involved in some particular products that we are getting in between the reactions. Okay, so that is why we are taking up these three compounds. CO2 is there in H2CO3 in the initial one. It broke down to HCO3 minus. It is there as well, and then it is there here as well. CO3 2 minus. Also, you can see the concentrations of CO2 that we got in each of these 3. It keeps on decreasing, right? Because it is getting consumed. In HCO3 concentration was 1. Here X, the HCO3 minus concentration we got is less than 1, 0.6761. Then in Y, it is even lesser than X, way lesser than X. So we will just add up these concentrations that will give us the final concentration of CO2 that is involved. Okay, So this is how we got here 1.676 molar. I hope this one must be clear. We don't need to discuss that to that much depth. So okay, here we have which of the following processes is associated with the emission of X-rays? Now what will be the answer? Which is associated with the emission of X-rays? I hope you all must be knowing this. What will be the answer here? No one knows this. What is alpha decay associated with? Let's get to it one by one. What does alpha decay give you? Alpha is radioactive decay. Actually, all these are radioactive decays itself, not only alpha. But everyone has some kind of products, right? Alpha particle is basically helium particle 2 4. This is the atomic number X. Okay, this is the mass number 4. Z, we represent it. We actually represent Z and X. We represent these two by Z and X. So Z is the atomic number. This is Z actually, and this is X. 4. So alpha decay releases alpha particle generally. All right. With beta decay, we have, what does beta decay has? One electron is released, right? And there is a gamma emission. So gamma rays are emitted. Gamma is basically 0 0. Here Z is also 0, X is also 0. So only Z gets like decreased by, not decreased, it will be actually E minus 1. It's because electron is released, so it will be minus 1 atomic number. So it will be added by 1. So the final product, it will have 1 added into it. So if I write it here, just so that you can solve other questions as well through it. In alpha decay, you have, let's say, and let's not represent it by X, let's represent it by A. Okay, the mass number. So here, let's say X, Z, and A you have. If it is going, this particular is going through alpha decay, it will have X, A minus 4, Z minus 2 plus alpha particle, right? Because alpha particle is He24. So here you can see from A, that is mass number, 4 will get subtracted in the product, and from Z, that is atomic number, 2 will get subtracted. Similarly, here in beta decay, we have X, A, Z. It will give you Y. A will remain as it is, Z plus 1. Okay, this is what I was talking about. Because it is releasing one electron and one gamma particle or gamma ray. So gamma is 0 0, electron is 0 minus 1. So here to get this minus 1 to release electron, you will have to add 1 in the atomic number in the product. So here this will be Z plus 1 A. Are you getting these 2 points so far? Are you getting these two? Please let me know.
Yes, sir. So actually, I know something like the beta positive decay and beta negative decay. So
Yes,
is there
there
any
is
difference
two.
between?
Yes, that is positron emission. Here you can see in the last we have positron decay, right? So this is positron emission. Positron is basically this E. Okay, not let's write it like this. E0 plus 1. Okay, so in this actually one electron is getting captured. In positron, in reality, one electron gets captured. Here we are emitting one electron, right? In beta decay. So this is the normal beta decay, and this is beta plus decay, and this is normal beta decay. So beta plus decay is nothing but positron emission. So positron gets emitted, that means it is actually capturing one electron. So here what is happening, if we talk about this positron decay, it will just get reversed. In normal beta
So
decay, it was
should
Z
minus
plus
one.
1. Yes, it will be here Z minus 1, because here it is having plus 1. Is it clear? Is it clear?
Sir, gamma ray.
Yes.
Sir, do we get gamma ray here? Because we get gamma ray in beta negative, that beta decay.
Yes, actually here also there will be, you can even write it and not write it, because it is 0 0, it doesn't matter. But yes, here also you get gamma rays. And also, like if I take an example, if you, let's say there is boron. Boron is undergoing positron decay, let's say. So it will turn into beryllium. Okay. Are you getting this point? This will, atomic number will decrease by 1. So how it is happening, this final thing? This is the positron emission, positron. Why it is happening? Because this boron is actually capturing one electron. Just calculate it from here. Here it is capturing one electron. Right? It will give B48. Are you getting this?
Yes.
Are you getting this particular reaction? So this is also known as electron, like here we also have electron capture. So these two you can get confused, but let me make it clear in the next step. You can get confused here that what is actually electron capture and what is actually positron emission. So positron emission and electron capture are like, they go hand in hand. In electron capture, what exactly happens is, that is given here in the C option. Let's get to that. So I will erase this part here. Okay, the question got erased, no issue. Okay, it won't get erased. Hmm. Okay, no issue. We'll write it here downwards. So this electron capture decay, what you are seeing here in the third option, this is actually fully known as K electron capture. This is the original name. And also we can call it electron capture. What happens is, you must know these things. Like there are different shells, right? In a particular atom. Let's say this is M, L, K. So K is the innermost shell. Innermost shell, right? Now here the nucleus catches electron. So what happens? I will show you. So this one what I showed here. So this is the electron capture. In this, positron is not getting emitted. In this, positron is getting emitted. So this is the only difference. And I will show you how. So electron capture and positron decay. This is the only difference. Here what happens is, in electron capture, we can take one example, like let's say x a, not a here, here it would be z a. This will capture one electron and this will give, here you can see it will be z minus 1 and a. So if we take one example, let's say for this silver 193.79, when it captures one electron, it gives platinum 78. So the atomic number gets decreased by 1. What was happening in this case? In this case also the same thing is happening, right? In positron decay, atomic number is getting decreased by 1. But here it is just the difference of emission. Here one positron is emitted. Here there is no emission. One electron is captured. This is the only difference. Here one positron is emitted. Positron is just the reverse of electron. This is electron and this is positron. Okay. This is emitted in case of positron decay. That is why it is named by positron decay. So this is beta plus. What is beta? In beta decay, what do we get? What is beta actually? In beta decay, what did we see here? Here one electron was emitted, right? In normal beta decay, one electron is emitted. One electron is released. In positron decay, one positron is released. In electron capture, one electron is captured. Are you clear with these three? All these three involve this E naught. All these three involve electron, but one involves positron, the other two involves electron, and this positron decay is actually emitting positron. This beta decay is emitting electron. This electron capture is capturing electron instead of emitting. Are you clear with these three?
Yes, sir.
Others, please let me know. Are you all clear with these three? Because these three can get confusing at times. I hope you all must be clear now. So where do we see X-rays? Where do we see X-rays?
Sir, maybe in electron capture.
Yes, exactly. Actually, in electron capture, that is why I didn't even write here somewhere. Yes, here. In electron capture, it is actually emitting X-rays with it. Record or class. It is actually emitting X-rays. Okay. So this is about electron capture. Now, did you get this, everyone? In this, you are getting alpha particle. In this, beta particle is getting emitted. Beta particle is nothing but gamma. Okay. In this, you are getting X-rays. In positron, again, you are emitting gamma rays. You are getting beta particle. Beta particle is actually combination of this gamma rays and electron. Alpha particle is the helium particle. So these are the basics: alpha particle, helium particle, beta particle. When you talk about particle, then it includes gamma rays plus electron. In electron capture decay, it captures one electron to give the final product with the emission of X-rays. In positron decay, it emits one positron not electron, but it emits one positron along with the gamma rays. So here the beta plus particle will be gamma rays plus positron. I hope this is clear now. Does this require any more discussion? Jaita, do you want to ask anything? You have written electron capture. I just saw the text. Yes.
No, sir.
Okay. 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 So maybe that you must have written for some answer. Electron capture. Okay. No issue. Then we will move on to the next question. The next question we have this one. Which one of the following radioisotopes has the longest half-life? So which one has the longest half-life? Does anyone know which has the longest half-life?
Sir, B.
BSM. Yes. Samarium. Actually, samarium has the longest half-life. I will provide some materials on this for individual systems. In what applications are these used? Individual radioisotopes, and what are the values of their individual half-lives. So I will also upload some materials on this because this will help you out. In some questions, they have asked the applications of some of these. So, like, if I say if I say like silicon, there is also parent and daughter isotope for that radionuclide. So these are like useful for dating biogenic silica, glacial ice. So likewise, we have application for each of these. For argon, you have groundwater, and also it is also helpful for glacial ice. Okay. So likewise, you have this for carbon and nitrogen. If we say it is used for dating biogenic carbon, calcium carbonate, all right, and in some meteorites. So this particular note I will provide with you all the notes based on this, so that you can go through the applications of each of these, and also at the same time you can go through the half-life values for each of these. Okay. So here for actually samarium, we have the half-life is 1.06 into 10 to the power 11 for SMND. The typical samples that include is pyroxene, amphibole. So all these kind of notes I will provide to you. So that sometimes actually this question number 4, you can see the fourth question is actually during that time it was 1 mark question. Now they have included all. They have included 1 mark, 2 mark. Now it is quite combined for gate. Earlier it was quite specified in the common section. Everything was 1 mark question that geology and geophysics candidates attend, and in the geology section everything was of 2 marks each question. But now they have actually combined everything. So the format has changed slightly. So now even if they have asked this in 2 marks, it's a pretty simple question actually. So you just go through that table that I will provide, that information, and from there you can get these questions right. You have to remember these. You don't have any other option. You have to remember the half-lives and applications and the rocks in which they are found. Okay. And also, Dibyesh, I think you can also appear for gate. Have you filled the form for gate? Because just today I recalled that from last year they have changed the criteria for appearing in gate. Now I think you can also appear for gate. Even bachelor's third year students can appear for gate. Have you filled up? Okay, you haven't filled up the form. No issue, but like what I believe you should have filled up at least. It's just that you would have gotten more practice and more experience in that. No issue even if you haven't filled up that. Because even if you have got some rank, you wouldn't have got anything because of the educational background criteria. You wouldn't have got any PhD or anything. So okay, let's get back to next question. The unit cell of an orthorhombic mineral. So these kind of questions also I have included here itself. The general chemistry question. This is from mineralogy, but this is actually from crystallography, but this is general chemistry question. As you can see, XRD pattern and all. Was compressed during deformation from 5 angstrom to 4.5 angstrom. So basically, this is an orthorhombic mineral. Orthorhombic mineral looks somewhat like this. Okay. This orthorhombic mineral, if we say along the C axis. So along C axis, this is C axis. Along C axis, it is getting compressed. Okay. Here it is 5 angstrom. It is going from 5 angstrom to now this is the compressed one. Okay. Along C axis. This is 4.5 angstrom. So you have 5 angstrom and 4.5 angstrom. Okay. So this is basically C1. This is C2, let's say. Okay, so these are the lengths. C axis is getting compressed. C1 is 5 angstrom. C2 is 4.5 angstrom. Now here actually for XRD patterns and all, Bragg's law is used, if you must have heard about it, with the other two dimensions remaining unaffected. So only C axis is getting affected. Other two is remaining unaffected. Okay. The absolute value of the shift in the position of 001 peak in its XRD pattern is. So it is asking about the shift in the position of 001 peak. Now 001 is a face of the crystal. So what do you think how 001 should look like? If this is, let's say, A, okay, let's say this is B and this is C. So where should I plot the 001 phase? This is plus direction, this is minus, plus, minus, plus, minus.
Sir, C plus direction.
The phase would be somewhat like this, right? It will be parallel to A and B axis, right? 001. There is no intercept on A, no intercept on B. There is one intercept on C. So here it will have one intercept on C, 1. So in 3D you can imagine it will be parallel to A and B axis. It will be parallel to this plane containing A and B axis. So this is a plane containing A and B axis. Okay, AB axis plane we can write here. So this 001 face is parallel to A and B axis and it is making an intercept of 1 on the C axis. Alright. So now let's see. This is the 001 phase. It is asking that what will be the absolute value of shift in the position of this phase in the XRD pattern. Okay. And it is asking in degree 2 theta. So remember this 2 theta, otherwise you can get it wrong. And also wavelength of X-ray used is given, lambda is given. For orthorhombic system, this value is given, this formula. So this actually is defined for this relation. This relation is actually for HKL. HKL is Miller index, right? So this HKL Miller indices are there. ABC axis intercepts are there, or axial length also we call it ABC. These are axial lengths. And D, what is D here? What is D here in this formula? Firstly, let us write Bragg's law. This is important, Bragg's law. I've seen a question coming from Bragg's law almost each year. If not each year, almost at alternate years. Or even like many years it's repeated. There is one question from this. They just change the form of question, that's it. What is Bragg's law? It is 2d sine theta is equal to n lambda, right? Where d is d spacing, diffraction spacing actually. D is actually d spacing. or you can say the during XRD, during the diffraction, the spacing that we have between two slits, this is D. Like there are these slits, right? Here the rays go. So this difference between these two slits is D. Okay. So if it is getting refracted, this ray that is coming over here, incoming rays, will get refracted from this surface and from this surface. Okay. Then we have different lambdas, different values, n lambda by 2 and n lambda plus 1 by 2. All these kind of things are there. So this is the basically what different wavelengths and path difference that we have. We will not go into details in this. This is just I show what is D spacing. So here in this formula for orthorhombic, please try to remember this relation H, K, L and D, this relation for basic crystallographic systems. Okay. For orthorhombic it is mentioned over here. Maybe sometimes they will not mention this. So here D is D spacing, ABC are axial lengths. Okay, axial length. HKL are Miller indices. For 001 phase, we have to see. Here it is talking about 001 phase. Okay. So now these are the basics that we have got over here. Now we will just simply use Bragg's law and this particular relation that is given. Wavelength of X-ray used is given 1.5418. So we will use it ahead. We will see. So for 001 space, 001 phase, not space. What is HKL? What is H? What is K?
0 and 1.
001, right? This is HKL. So we will just simply put this in this formula and we will define D for 001 phase. What will be D? So let's see. 1 by D square is equal to, this will come out to be 0, H is 0, K is also 0. What is L? L is 1 square divided by C square. So what relation are we getting from here? D is equal to C, right? D spacing is equal to axial length on C axis for 001 phase. So we are just calculating for 001 phase because it is asking only about that. So we get D is equal to C from here. Okay. What is D1? We have two conditions, right? This is the one condition. This is the second condition. We have C value, but C1 value is there and C2 value is there. And we have to find the difference, absolute difference when it is turning from actually from C1 to C2, not C2 to C1. When it is turning from C1 to C2, then what is the absolute difference in shift in position of the peak? Okay, so don't go too much into the details of each terms. Just look here what is happening, how to get through these questions. So it is going from C1 to C2. Now D is equal to C. So now D1 is 5 angstrom. That means the D spacing in first case, undeformed one, is 5 angstrom. And when it is getting deformed or compressed, then D2 is 4.5 angstrom. So we get D values for both the cases, right? Now we will use the Bragg's law. Bragg's law is 2D sine theta is equal to n lambda. So for first case, 2D1 sine theta 1, there will be some other angle value is equal to n lambda. Lambda would be the same because X-ray it is using, and lambda of X-ray like it would be the same, right? So this will give us, here n value is 1. Why the n value is 1? Can anyone tell me? What is n lambda and why n value is 1? Here. Why can we take n value as 1? Anyone? So n here is actually the order, the path difference order. So if there is nothing mentioned for n, we just assume it to be the first step, the first order. Okay. So since here in the question itself there is nothing mentioned for n, that which order diffraction it is happening. So we take n as 1, because otherwise, like even if you take half or anything, for both the cases it will be half, right? So answer would come out to be same. So n eventually will get cancelled out. So you don't need to worry about it, but still to make calculation simple, you just calculate it for first order diffraction. So simply put n as 1, because nothing is mentioned. If there was something mentioned, we would have taken that into account. So here the first equation, this for first case, it becomes 2, what is d1? 5 angstrom sine theta 1 is equal to, what is lambda? Lambda is given as 1.5418 angstrom. 1.5418 angstrom. Okay. This we get the first equation. Similarly, the second equation will be 2, d2 will be 4.5 angstrom sine, here the angle will be theta 2, and this will be the same, 1.5418 angstrom. This is the second equation. So now let's calculate each of these theta 1, theta 2, and this is what we need to get. We need to get theta 2 minus theta 1. So that will give us theta, but here it is asking in question degree 2 theta. So we will just multiply it by 2 times. Okay, so don't forget this degree 2 theta. This is crucial. So now what we will get from here? Theta 1 will be sine inverse 1.5418 divided by 2. Actually it won't be 2, it will be 2 into 5, 10 divided by 10. Similarly, theta 2 will be sine inverse 1.5418 divided by 4.5 into 2 is 9 divided by 9. So can you calculate these two values? What will be theta 2 minus theta 1? Therefore, theta 2 minus theta 1 would be, this Bragg's law question can even come in IIT-JAM, so this is quite probable over there. They have even asked this many a times in IIT-JAM. Just let me calculate this. Okay, so this will come out to be theta 2 minus theta 1 is coming out to be 0.99445, right? Yes, Dipesh, right. So here it is asking for 2 theta, so we have to multiply by 2. Now most of the people in the exam would have got up to this point right, and they would have like entered this as answer, but this will be wrong. The answer will be 1.999 something. So up to how many decimal places have they asked? Up to 3 decimals. So it will be 1.999. So this is what the answer will be. Okay, this is the absolute difference, but it is asking for degree 2 theta. For 2 theta, we just have to multiply 2 with the final theta value. Did you get this, everyone? How did we solve this? How we used Bragg's law? We have these this formula was given to us. We used each of the values. For 001 peak, we took HKL Miller indices. Did everyone get this? Please let me know for once. It is asking degree 2 theta, so we will just multiply 2 towards the end. I hope that question was clear. Okay. 1.9984. Yeah, like you can see, whatever it is, it may be 1. Like I just approximated it earlier. So maybe it may be 1.998 then. Okay. If you round off, it would be 1.998. If it is 4 after 8, then rounding off will give you 1.998. Okay. So if it was like this 8 4, if it is this case, if this fourth decimal place would have been greater than 5, then we would have taken 9 as the third decimal digit. So this rounding off, like I think you all must be knowing this already, how to round off. So moving on to the next question. This is clear as you people are telling. So we will move to the next. Here we have the abundances of the isotopes 35 Cl and 37 Cl. So these are the isotopes basically for chlorine. So the basic definition of isotope is that the mass number differs, the atomic number remains the same. All right. So atomic mass is given for Cl35, atomic mass is given for Cl37. Abundances of isotopes, this is given 75.77%, 24.23%. The calculated atomic weight of Cl is dash AMU, round off to 3 decimal places. Now atomic mass for Cl35 is given, atomic mass for Cl37 is given. The calculated atomic weight of Cl it is asking. So what shall we do here? It's a simple arithmetic question. Nothing much to do here actually. Atomic weight of Cl will be 35 Cl into 75.77 percentage plus 37 Cl into 24.23 percentage. Is it correct? Whatever I have written over here. By basic
Yes,
sense.
sir.
Huh? Sorry.
Yes, sir. The formula is right.
Yes. So this is also from the basic sense, right? From basic sense, what do you get? Even if you don't know the formula, from basic sense, there are two varieties of Cl. One Cl variety is accounting for 75.77%. One Cl variety is accounting for 24.23%. And when you add this 77.77 and 24.23, it is coming out to be 100. That means the overall Cl atomic weight, what will it be? So this is the basic maths that you do. Even if you don't know the direct formula, this is the basic maths. You take the percentage of one variety, then you will add it with the percentage of second variety, then you will get the overall one. So here we have 34.96885. Units is already in AMU, that is given. So overall unit, the answer will also come out to be in AMU. You don't need to worry about units here. Divided by 100 plus 37 Cl is given to be 36.96590. Actually here it will be atomic weight. Okay, atomic weight of Cl35 and atomic weight of Cl37 into 24.23 by 100. So this is a simple calculation from here. This was I think asked in 2 marks. So this was a simple 2 marks that was handed over that year. Which year question is it? 2020. Okay, just 2 years back. So here now you can do the basic maths, I reckon. It will be round off to 3 decimal places. So instead of wasting time over here, you can take it as homework. You can just calculate this from here, and whatever answer is coming out, just match it with the answer key and then tell me if it was right or wrong. Okay, if it was wrong, then we can discuss. I like what I believe, this is a simple calculation, it would be right. Okay, after calculating from here, so you just do it yourself. Moving on to the next question, because we don't want to waste too much time in doing the basic arithmetic stuff and all. Okay, so the next question we have here is question number 24. A source rock undergoes melting. All right, source rock is undergoing melting. Assuming batch melting. Now, there are a few things that you will keep on getting this in geochemistry. That is batch melting, equilibrium crystallization. I'm just writing these here. And as we will keep on encountering these in different questions, we'll keep on discussing these. There is fractional crystallization. And then there is Rayleigh fractionation. So if you haven't gone through like geochemistry a lot, I can tell you these are the 4 conditions that are more prominent. Just this is your work for today. Just write Cl by C naught formula for each of these and what will be the F value for each of these. Okay, how F is differing, how Cl by F is uh, fractionation basically, how F is differing, and how Cl by C naught formula is differing for each of these cases. So write these down and remember these for each of these. For batch melting, for equilibrium crystallization, for fractional, for Rayleigh fractionation. Okay, so do this by yourself. Just a simple homework for you all. Because the questions keep on they just keep on rotating questions between these conditions. Okay, it will get deleted. Okay, no issue. Okay, so here we have in the question it is telling about batch melting. 5% partial melting and bulk distribution coefficient is 0.045. So here F, as I said, is fractionation. From 5%, this is the F value that is given. 5% partial melting means F is now 0.05. Okay, 5% means 5 by 100. We always take it as fractions, not percentage. So 5% means 5 by 100. 5 by 100 is 0.05. F value is given to you. Then bulk distribution coefficient is given to you. Bulk distribution coefficient is di bar. So most of the times you need to calculate di bar, but here this question is actually simple since di bar is already given to you. So di bar is 0.045. Okay. Now the question is pretty simple. These two things are given to you. It is directly asking Cl by C naught. So the formula for this, for batch melting, I am writing it over here. Cl by C naught formula for batch melting is 1 whole divided by, these things you need to remember, and this will come by practice. Just keep on practicing questions on these. If you don't remember, then you will not even be able to start the question in the exam. 1 minus F plus F. So this is the formula, alright, and this is for batch melting. Now you can just simply put the values. This is actually an easy question, as I mentioned, because here di is already given. In most of the scenarios, you need to calculate di bar. Di bar is the summation of individual di values. So here you will get Cl divided by C naught. This is what it is asking the question, the enrichment factor, Cl by C naught. So this is the enrichment factor. Write it here. Enrichment factor. 1 divided by di bar, you have 0.045. 1 minus F, you have 0.05. plus F you have 0.05. So the calculation, this will come out to be, here I will write it, 1 minus 0.05 is 9.95 into 0.045 plus 0.05. This value is 1 divided by this. So this is coming out to be 10.78. Up to how many decimals? I think 2 decimal it must have asked. Yes, round off to 2 decimal places. So 10.78 is the answer for this. So this was a pretty simple question, direct formula based. Nothing much here and there. Di value is given, F is given, everything is given. Is it fine?
Yes, sir.
Okay, so we'll move ahead. As I mentioned, just remember this CL by C naught formula actually differs for each of these cases. So just remember for each case. Okay. Now in successive questions also we may get for equilibrium crystallization, we may get questions on fractional crystallization. So we'll keep on discussing while as we keep on getting those questions. Okay. Question number 25. If delta H of formation of CaSiO3, SiO2 and CaO from calcium, silicon and oxygen are respectively. So this is the delta H values given. Okay. The enthalpy of formation of CaSiO3 from CaO and SiO2 is dash kilojoules per mole. So it is asking about enthalpy of formation, okay, from actually CaO and SiO2. So firstly, let's see, let's just write it in reaction form. We have SiO2 plus CaO giving us CaSiO3. Okay, this is what we are getting from this reaction. Now delta H values are given. Delta H G we will write. Delta H values are given in kilojoule per mole. For SiO2, how much it is given? Minus 911. For CaO, it is given minus 635. For CaSiO3, minus 1635. Okay. So what is the enthalpy of formation or enthalpy of reaction? If we say delta HR, enthalpy of reaction or formation, these two are same actually. So what is, because it is formation of CaSiO3 and it is forming through a reaction. So enthalpy of reaction and enthalpy of formation are same. So you can even write it as delta HF or delta HR. So what will this be? I don't think you all remember the formula. I will write it here. So since this is the revision course, we will keep on revising these things. Even if it's your first time, it doesn't matter. You can get these things right. Okay. H minus summation Bi to FH. So just mark it here. This part is for products. This part is for reactants. So basically enthalpy of formation or enthalpy of reaction is enthalpy of products minus enthalpy of reactants. Now this AI and Bi is nothing but the exponents that are used in the reaction. Here everywhere it is 1. So we don't have to take care of AI and Bi, but I am writing this general formula. This is the general formula for enthalpy of reaction. I will write. So this is the general formula, okay? That is why I have written AI and Bi. AI is, if here, let's say it was 2, so we would have multiplied 2 with delta HF for this products part. Okay, but here it is nowhere. Here actually it is 1 everywhere. So it is a simple one. So now using this formula, what do we have? We just have to calculate this delta HR, and it is asking in kilojoule per mole, and each of the values is already given in kilojoule per mole. So it doesn't matter. We don't need to worry about the units. Here we have 1 into what shall I write here? Delta HF for products. Please tell me what shall I write here?
Sir, minus 1635.
Yes, absolutely. Minus 1635, then minus 1 into minus 911. This is for SiO2 plus 1 into minus 635. So this square bracket, this is having for reactants. Delta H for reactants. Okay. This will be plus in between. We'll add the delta H values. So now it is a pretty simple one. Now it is just about calculation. This is minus 1635 minus minus, this will become plus 911. This minus minus will again become plus 635. So what will this come out to be? Minus 89. Okay, minus 89 kilojoule per mole. So no decimals, nothing. It's a direct number. That is why it is not mentioned up to how many decimals. It's minus 89. And while typing these answers, you have to type minus also. If you miss minus, you won't get the marks. So in scientific calculator, when you use the numeral keypad that is provided in the exam, when you fill up the answer for this, you will have an option to fill minus in the beginning. So always remember that, put minus 89. Don't miss the minus, otherwise you won't get the marks. So there are many answers that involve the negative sign. So never miss the negative sign. All right. So I hope this is also clear. It's a basic thing: enthalpy of reaction, enthalpy formation. As you can see, as we are discussing different questions, we are discussing different concepts as well. Basically, different formulae for that are involved in thermodynamics, and the working methodology, how those formulae are used to get the answer. So these two things will help you all to solve all the questions from geochemistry. You will not miss any question from geochemistry. And in geochemistry, easily 3 to 4 numericals are there. As you can see, this is still 2020 going on. So in 2020, how many numericals did we solve? 2 MCQs were there. Then one, okay, that let's count it in mineralogy. 1, 2, 3. 3 numericals and 2 MCQs were there. So all these numericals, like by looking at the question numbers, these are of 2 marks. So 6, and I think one of the MCQs maybe of, okay, so this is from geology portion only, and in 2022 this was not separated. So total 10 marks of geochemistry questions were there in 2020. So around 10 to 12, 14 marks sometimes they keep on asking. So these are easy 10 marks. You can see just straightforward formulae we have applied, and then we have done the calculations. Up to now everything is clear, right? Just put one confirmation and we'll move to the next question. So we have solved for 2021, 2020. Now moving on to 2019. 2019. Okay, so here we have a question: which one of the following clay minerals contain potassium? What should be the answer? All these are clay minerals: illite, kaolinite, montmorillonite, and vermiculite. Which contains potassium? Actually, the first option will be the correct one. Illite contains potassium, K. Okay. Kaolinite contains aluminium because its formula is somewhat like this: AlCH2Si2O5, somewhat. And these are actually complex formulae, chemical formulae, so you don't need to remember the complete chemical formula for each of these. but you need to know the elements that are there. Montmorillonite actually contains Mg and Fe, and vermiculite contains NaCa, the alkali metals, alkali elements. So this is what these four options is all about. So potassium is there in elite. Okay. So this A would be the answer. Moving on to the next one. Question number 10. Which one of the following sequences of minerals correctly list an increasing rate of dissolution during chemical weathering? Increasing rate of dissolution.
Sir, B.
We will see increasing rate of dissolution. Now, what is the name of the reaction series that gives this? Does anyone know?
Bowen's reaction.
No. Actually, Bowen's reaction directly doesn't give this. This is defined by,
Goldwich.
yes, Golditch dissolution series. Now, actually, Golditch dissolution series is actually the exactly opposite of Bowen's reaction series. So it is not directly defined by Bowen's reaction series. It is defined by Golditch dissolution series, which in turn is exactly opposite of Bowen's reaction series. So basically, you just need to remember the Bowen's reaction series. That's it. So now, what will be the answer? Someone mentioned B. So actually, B will be the answer. So increasing rate, you can see the increasing rate is quartz, orthoclase, pyroxene, olivine. So dissolution increases from quartz to olivine. Is it clear?
Yes, sir.
So here again we have a typical geochemistry question. This is actually from isotope. So this involve isotopic. So like what do we have here? Given that oxygen 18 to oxygen 16, V small value is given. V small is equal to 2000 like 2005.2 into 10 to the power minus 6. The O18 by O16 of a sample whose delta O18 V small is 25 per mil. This is actually, this you can see here, it is not percentage, but it is like this. So this is known as per mil. Per mil, okay, is dash into 10 to the power minus 6 round off to 1 decimal place. So this is again like, this is actually a basic question. Okay, this involves just a bit of calculation, and this is actually formula driven. This is from VSMO and this is formula driven. So we will just see what formula can we apply over here and how can we directly get onto this. So such kind of questions I don't think so we have discussed so far, but we will see here. So VSMO is actually a standard value. Okay, does anyone know what is VSMO? What is this?
Sir, this is the value for O18 by O16 in ocean water. They're taken as standard.
Yes, what will be the full form of this? This is an abbreviation, right? VSMO for some full form. What will be the full form? It won't be asked in GATE obviously, but just generally I'm asking. This is actually Vienna. Vienna is a location. Vienna Standard Mean Oceanic Water. Okay, so earlier it was just SMO, then they added Vienna because from Vienna they just took the standard values from there. So Vienna standard mean oceanic water, this is VSMO. Okay, so yes, as you rightly mentioned, this is the O18 by O16 value in the oceanic water. So let's see in the question. If you want, okay, I will keep this for reference in the final PDF. So we'll solve it here. Otherwise, I would have erased it because the final annotated slide is also getting uploaded. So whenever I'm erasing something, if that is having some information, let me know so that I don't erase it and I keep it in the final PDF. So final PDF is useful for you to go for a quick revision, quick revision, because if you again go for videos like again the recorded lecture, it will take a lot of time. So instead, just go for the annotated slide. You will recall each and everything what we have discussed in the class. So here we have basically O18 by O16 VSMO as 2005.2 into 10 to the power minus 6. Okay, this here is actually our standard. This is our standard. I will let you know what is our standard and what is our sample. This is our standard, and then we have, it is asking about O18 by O16, O18 by O16 dash into 10 to the power 6 minus 6. Okay, this is our sample. So firstly, this is our sample when one more condition is given, when this delta 18O VSMO is 25 per mil. Okay, here it is plus, actually plus, yeah, it is there. So we have what is the formula for delta O18? Has anyone gone through all these parts? What is the formula for delta O18?
So it's the value of O18 by O16 in sample minus O18 by 16 in standard divided by standard.
Okay, so here we have written this O18 by O16 as R standard, and in basically the standard one, and O18 by O16 in sample we have written as R sample. So just to simplify, this is delta O18 is R sample. So I will not write it as this, otherwise it will create confusion. Just one second. R and then subscript as sample minus R standard divided by R standard into 1000. We also multiplied by into 1000 because of the units. Okay, we multiplied by 1000 because of the units per mil. So this is what the formula is that we have to use over here. It's actually a simple case. Just one second, the page is not loading. Yes. So okay, now just have a look at this formula and remember this formula. Whatever I am highlighting the formula that you need to note down and you need to remember, otherwise you won't be able to solve the questions. Okay, delta O18 is given to you 25. So this 1000, since we have written over here already, we will not write here 25 by 1000. Okay, because delta O18 is given 25 per mil, so we could have written 25 by 1000, but since we have already written it on the RHS, we will not write it here. Is equal to R sample, let's write it as R. This is what we need to find out, minus R standard, you know already, it is 2005.2 2005.2 into 10 to the power minus 6 divided by 2005.2 into 10 to the power minus 6 into 1000. Therefore, what will be R? R will be 25. Actually, this 25 by 1000. Okay, let's write it. No issue. 25 by 1000 into 2005.2 into 10 to the power minus 6 plus 2005.2 into 10 to the power minus 6. So we have just taken R on one side and other values on other side. So this will come out to be. So this complete calculation we can do at once. We can just take out 2005.2 outside. Okay. Then what will we have? This 1000 and this 10 to the power minus 6 will become 10 to the power minus 9, right? Plus, so we will also take 10 to the power minus 6 outside. Either minus 3 would be there. Since it is already asking in 10 to the power minus 6, we will keep this aside. Okay. The rest of the values we need to answer. It is already given into 10 to the power minus 6. So here we will have 0.025, 1.025, right? This will be 0.025 and then plus 1 is 1.025. So now just multiply these two terms, 2005.2 into 1.025. This we need to answer into 20 power minus 6. This we need to answer up to 1 decimal place. Yes, 1 decimal place. So what will this come out to be? This will be 2055.3. So this is the answer, okay, into 10 to the power minus 6. So this is the answer, 2055.3. All right. Is it clear up to now?
Yes, sir.
Okay. So you have to remember certain formulae, you have to go through certain formulae, you have to remember this delta O18 and how V SMO, how R standard, R sample, how these are taken. So these things you need to go through by your own. Otherwise, you won't be able to solve the questions. As you can see here, this was a pretty simple question. Each and every value is given. You just need to put them in the formula and that is done. You get the answer directly. So it is actually quite simple question. If you just know the formula, you can easily get the answer and get 2 marks here. So, okay, moving on to the next question. Choose the correct combination for the following two statements. Correct combination for the following two statements. Okay. So, there is statement 1, there is statement 2. Statement 1 is 4 elements that make up about 90% of the bulk earths are Fe, O, Si, Mg in decreasing order. Statement 2 is 4 most abundant elements in the Earth's crust in decreasing order are O, Si, Al, Fe. Now tell me the answer. What would be the answer? These two statements are both correct or are both wrong, or which one is correct, which one is wrong?
Sir, I'm sure about statement 2, that is correct, but not sure about statement 1.
Why? Actually, both the statements are correct over here. Now see what is happening here is A would be the answer. Both statement 1 and 2 are correct. Statement 1 is talking about bulk earth. Okay. Bulk earth, that means it is including the complete earth. So where are you getting the confusion here? Bulk earth is having actually Fe in the most abundance because of the core. Core is formed of Fe. Then we have simply the almost the similar one. Mg here exceeds Al and Fe because Mg is there in, as you must have heard, Mg perovskite and all. Mg is there in mantle a lot. Okay. So this is the like decreasing order of abundance when it comes to bulk earth, complete earth when we are talking. Fe exceeds everything because it is there in proportions, in huge proportions in core, and core is having very like good volume, considerable volume. And then the second statement is talking about earth's crust. It is just talking about earth's crust, not mantle and not core. So in earth's crust, oxygen is the most abundant, then we have silicon, then we have aluminium, and then we have iron, and then we have Mg and so on. Okay, so on and so forth. So this is for earth's crust. In crust, oxygen and silicon are the most abundant ones. That is why we have silicates. Silicates in crust, we found a lot of silicates, right? Then we have aluminium. This is because of the sedimentary cover, the sedimentary rock cover. Same is the reason with Fe here in crust. Okay. Then we have Mg and then Na, Ca. It goes on. Okay. So for bulk earths, this is because of core. Then oxygen is there throughout. It is there in mantle also. It is there in crust also. Okay. It just keeps on changing forms up to spinel. In mantle, it keeps on changing from ringwoodite, perovskite, then it moves on to spinel. Okay. So Si is again, it's there. And then Mg exceeds these two because Mg is there in huge proportions in mantle. So when we talk about bulk earth, then Mg exceeds Al and Fe. And when we talk about only crust, so this is the case. I will again put up one list of decreasing order of abundance of elements for many categories. Like what all you need to know, I will write it here. And I will put up the list for this. If I miss, then please remind me. I will put this up. Decreasing order of abundance of elements, let's say. So for what you need to remember this thing, you need to remember for crust. You need to remember for, actually in crust, you need to remember for oceanic. It's not like you need to remember, but you can remember for your sake. For continental, it won't differ much. Okay. And also for bulk crust. So here three parts are there: crust overall, oceanic, continental. Then we have core, or not core actually. We have bulk earths. Okay. They may ask for crust plus mantle. So then you need to know what can exceed what. They may directly write lithosphere. So in lithosphere, actually only uppermost part of mantle is taken. Okay, so what effect can it have? You can calculate or you can have a look. They may ask for, let's say, what other things are there? Solar system. Or they even write universe. What elements are there in universe? So it starts from hydrogen, helium, so on. Okay. So what is left with? What question they can ask around this order of abundance of elements? These things are there. Anything more can be formed? Any more question can be formed? Any more part? So if you cover all these things, wherever they are asking this decreasing order, you can easily tackle that. So if any more is there, let's say, right now I am not able to recall. If any more is there, I will just put it up and compile. So oceans also, they have included elements in oceans. These kind of things are there. We can just go through it. Okay. I will upload a list on this. Actually, in some of my notes, I don't know, somewhere it is there. I will have to find it. I have a proper notes of this. I made a proper list of all these decreasing order of abundance of elements and wrote it like on a single page so that we can recall it. So, okay, moving on to the next question. Choose the correct combination for the following four statements. Again, here four statements are there. Statement 1, anhydrous partial melting of peridotites produces basaltic magma. Okay. Statement 2, hydrous melting of peridotites produces andesitic magma. 3, congruent melting of minerals produces liquids of composition identical to the minerals. Statement 4, incongruent melting of minerals produces liquids of different compositions and new solids. So what do you think? What should be the answer in this question? Question number 34. It tests your basics a bit. Does anyone have any idea what can be the right answer over here? No one has any idea? Okay. Actually, in this particular question, firstly, let me tell the answer, then we will come to each statement. All four statements are correct. Are okay, it is incorrect. Actually, the A will be right. All four statements are correct. Okay, D option is for incorrect. So, in this particular question, all four statements that are given are correct. Now, with this first statement, let's see. Anhydrous partial melting of peridotites produces basaltic magma. Now, this is how actually basaltic magma is produced. Basaltic magma is actually produced by anhydrous partial melting of peridotites. That means the melting of peridotites will take place, but it will be an anhydrous melting. Anhydrous means it won't include water. It won't produce water. Okay. So this is how basaltic magma is produced. Like this is a basic production of basaltic magma. This is produced by anhydrous partial melting of peridotites. Second statement again, this is also same. I will write it here. I'll just draw it here rather. Let's say this is subduction zones. And here, from here, due to heating, you get water flux. Okay, H2O flux. So what happens is this H2O flux forms andesitic magma over here. This is andesitic magma. So this is the second statement actually. Hydrous melting of peridotites produces andesitic magma. So this is the hydrous melting because of this you get water flux, right? Because of the melting over here. The pressure is suddenly increased for the subducted plate, and then because of that melting, here some volcanic chain would be produced. This volcanic chain is of is andesitic in nature, and this andesitic magma is the result of hydrous melting of peridotites. Here the melting that is happening is hydrous melting because it is resulting because of water. Okay, water combines with magma and then it melts, combines with peridotites. So this is what happening in the second statement. Third statement. Now, what is congruent melting and what is incongruent melting? Do you all have any idea about it? I will write it here. Incongruent melting, mineral directly produces the melt. Okay, and and let's write it here only. In incongruent melting, mineral produces a melt plus another mineral. So another mineral is formed, but melt is left out. So this is M2, this is M1. This happens in incongruent melting. And here mineral directly produces the melt. No other mineral, nothing of that sort. Incongruent melting. Do you get this? Incongruent melting. This congruent melting of minerals produces liquids of composition. Liquids of compositions identical to the mineral. So this liquid of composition identical to the mineral. This is what statement 3 is. And then statement 4, this incongruent melting produces liquids of different compositions. Okay, this liquid will be of different composition here, and new solids. So this is what this fourth statement is saying. Liquids of different compositions and new solids.
Sir,
Yes?
sir, equilibrium melting and fractional melting वो उसी के रिलेटेड में आता है क्या? वो
सॉरी,
अलग है?
इक्विलिब्रियम मेल्टिंग, फ्रैक्शनल मेल्टिंग, क्या बोला आपने उसके बाद?
वो कॉन्ग्रुएंट एंड इनकॉन्ग्रुएंट मेल्टिंग से रिलेटेड में आता है, रिलेटेड में आता
एक्चुअली
है
वो
क्या?
दोनों टाइप अलग है और ये दोनों टाइप अलग है, टाइप्स ऑफ मेल्टिंग. इक्विलिब्रियम मेल्टिंग में लाइक इट्स अ स्लो प्रोसेस मेल्टिंग एंड like it's reversible, right? Equilibrium melting mein if we talk, let's say M1 plus melt 1 gives M2 plus, not melt actually, yes, melt only, melt 2. So this is the magma part, melt 1 melt 2. This is the solid part, mineral. अभी equilibrium melting अगर होगी, so it will be reversible, right? So equilibrium melting cannot be congruent melting actually, or actually in some cases it is there. Like if you study ahead, in some cases, because equilibrium melting में क्या है, it totally depends on the pressure temperature conditions. Now अभी मान लो आपकी there is some magma, okay, basaltic magma से no, this is actually mineral this side. So कौन से मिनरल से हो सकता है? लेट्स से ओलिवीन है, ओलिवीन से ड्यूनाइट का आपको मेल्ट मिला. नाउ इफ यू अगेन bring the pressure temperature condition to this melt to solidify it into some mineral, it will solidify into olivine. Okay, so ये reversible है. Like just depending on the pressure temperature condition, if you make pressure temperature such that olivine mineral gets completely melted, तो वो dunatic magma दे देगा. Now if you have dunatic magma and if you bring the pressure temperature such that it crystallizes into some mineral, so it will give you olivine. So now this is reversible. Okay, so reversible can be congruent, and again reversible means equilibrium जो मैं बात कर रहा हूँ, equilibrium crystallization या equilibrium melting. Equilibrium melting can be congruent and can be incongruent both. Mostly incongruent होता है ये. Congruent is only in some cases, like dunite आपको पता है कि वो olivine से बना है. So there are only some cases where a complete melt can have only one particular mineral constituent. I hope you are getting my point. Not all types of melt have only one particular mineral constituent. They have different mineral constituents, right? They can form olivine, pyroxene, amphibole. Now, for example, basaltic magma. Basaltic magma can form n number of minerals. Like it can form pyroxene, it can form amphibole, it can form biotite, it can form quartz. So these kind of magma are very less, which can have only one type of mineral. So for equilibrium melting or equilibrium crystallization to be congruent, it will have very rare cases. Mostly it is incongruent melting or incongruent crystallization. Same जो आपने second बोला fractional crystallization, fractional melting. Fractional crystallization is nothing but it is crystallizing in fractions. So this fractional crystallization goes hand in hand with incongruent melting, because incongruent melting में भी यही हो रहा है. Your mineral 1 is now melted into another mineral. So अगर आप इसको reverse कर दो, okay, let's say I think I need to add one more page. Just 1 second. Now see, for fractional crystallization, let's say crystallization is a different thing, melting is a different thing. Actually these are reverse process of each other. let's say for fractional crystallization. Fractional crystallization means you have some melt, you have some melt, and let's say you have some mineral over here that is already formed, mineral 1. Now if this is giving you, not melt, if it is crystallizing, if this is giving you mineral 2, right? Some other mineral will be formed utilizing this melt and mineral 1. So now this is actually incongruent crystallization. This is the form of incongruent because new solids you are getting here. Although congruent and incongruent terms are not used for crystallization, these are used for melting. So इसी को आप reverse कर दो, this will be fractional melting. Okay, fractional melting. So fractional melting में you will have some mineral, mineral 1, which will give melt, plus let's say you stopped it at certain temperature pressure and this mineral did not melt up to that pressure temperature. Okay, ये एक certain PT पे हुआ होगा, and this PT पे let's say some part of this mineral 1 got into like converted into melt and some part remained as solid, and this to be converted into melt will require further temperature. Okay, further increase in temperature and pressure. So let's say ये condition मिला आपको fractional melting में. Now this is the condition of incongruent melting, because now here you are getting mixed compositions of liquid and also another solid, new solid you are getting. Same if I talk about equilibrium melting. Equilibrium melting. Then for equilibrium melting, let's say equilibrium melting mein it will always be a reversible reaction. Okay, because there is an equilibrium maintained between those two. So equilibrium melting, let's say we have mineral 1 converting to, now see, this is what I was telling. In equilibrium melting you can get two types of conditions. In fractional you will always get incongruent. In equilibrium you can get congruent and also incongruent, but mostly it is incongruent. Congruent, as I said, only in some cases. How? We will see here. After this mineral converting into melt, it will transform into melt, right? And plus actually some other mineral would also be there. So this is what the case of equilibrium melting. In most of the cases this forms incongruent. Okay, let's say this was basaltic magma. Not okay, it is only mineral. So mineral 1, let's say it is pyroxene. Okay, pyroxene. So there will be some melt. After melting it will have some melt containing pyroxene. It can also produce some mineral out of it which will have pyroxene along with some other things, because here actually in this equilibrium melting we also write melt 2. It will melt only after meeting with either water, so this can be either water, okay, or this can be either any other melt that will combine with the mineral 1 and will make it to melt as well, this one. So here this pyroxene will have some other constituents as well to form mineral 2. So this is the incongruent melting again, but same thing can happen here. Let's say olivine is there. Now let's say only olivine is there, and along with like by just temperature pressure, not including any fluids, by temperature pressure change, we melt this particular mineral. So it can give you diunitic magma, though there is nothing as such specific. You must haven't heard this specific thing, because that is why I said now this is the case of congruent, and that is why I said this is very rare, very rare. That is why never it is heard and nothing of this sort is there. Is it clear, Akshay? Both these are different things, but yes, they are related a bit.
हाँ सर, समझ गया.
So I hope this question is also clear to you all. Mostly congruent and incongruent is not used for like crystallization. It is used for melting. There is congruent melting, there is incongruent melting. Congruent melting is just that the solid completely converts itself into the melt and the composition remains same for both the sides. And in incongruent melting, the solid will convert into melt, but it will produce a new solid and the composition will differ. The melt will have different compositions, the new solid will also have different composition. So okay, let's stop it here. Like it's been more than 2 hours. We'll continue from here. Here again, you can see there is one question, and this question is involving batch melting again. So again, the formula is given over here. So, but this is a different type of question. Here KD values are there. So here we need to calculate DI bar, that is bulk distribution coefficient. So here we need to calculate this separately. Bulk partition coefficient, bulk distribution coefficient, all these things are there. So this question from here, we will have a look in the next class. It's already more than 2 hours. So let's call it a day for today. Is there any doubt, any question? Any question